Hello everyone, my name is Sudheer Kumar, working as an assistant professor of mathematics, MLR Institute of Technology. Today's lecture, I am going to cover about beta function and its properties. Right, let us see the actual definition of beta function. So, beta function is special function which is denoted with b of m comma n, and it is defined as integral 0 to 1 x power m minus 1 into 1 minus x whole power n minus 1 dx, where m is greater than 0 and n is greater than 0. Right? So, this is a special function. The problems which we can do at intermediate level, if any of the problem cannot be solved using those formulas, then we use this special function called beta function. Let us see the properties of beta function. First property is prove that beta of m comma n is equal to beta of n comma m. Let us prove this result. First consider LHS part, beta of m comma n. By definition we can write it as integral 0 to 1 x power m minus 1 1 minus x whole power n minus 1 dx. To prove this result is same as beta of n comma m, let us take 1 minus x is equal to y. So, this implies minus x is equal to y minus 1. So, x is equal to 1 minus y. If x equal to 1 minus y, if we differentiate both sides, dx is equal to minus dy. So, substitute this lower limit of x equal to 0 here. So, we get whenever x equal to 0, we get y is equal to 1, and upper limit whenever x is equal to 1, substitute x equal to 1 here. So, we get y is equal to 0. So, this integral can be written as beta of m comma n is equal to integral 1 to 0 x power m minus 1, x means what? 1 minus y whole power m minus 1 into 1 minus x. 1 minus x means y power n minus 1 into dx. dx means minus dy. Right? So, in this integral, if we remove this negative sign, the limits will be interchanged. Right? So, this can be written as integral 0 to 1 y power n minus 1 into 1 minus y power m minus 1 dy. So, this can be written as beta of n comma m. So, beta of m comma n is same as beta of n comma m. This result is done. Say for example, if beta of say 5 comma 10 is always same as beta of 10 comma 5, right? Even if we interchange m and n values, it doesn't affect the result, right? Let us see the next result. Prove that beta of m comma n is equal to 2 into 0 to pi by 2 sine power 2m minus 1 theta and cos power 2n minus 1 theta d theta. So, let us prove this result. To prove this result, let us substitute x is equal to sine square theta. Now, both sides if we differentiate, I can write this as dx is equal to sine square theta derivative is 2 sine theta into derivative of sine theta is cos theta d theta, right? So, this by definition we have beta of m comma n is equal to integral 0 to 1 x power m minus 1 into 1 minus x whole power n minus 1 dx. We prove this result by basic definition of beta function. Now, in this substitute x equal to sine square theta and dx is 2 sin theta cos theta d theta. So x values will be converted to theta. Now what is the lower limit of x here? X is equal to 0. Substitute x equal to 0 here. So sin theta is 0. Sin theta is 0 only if theta value is 0, right? And upper limit, if you take x equal to 1, substitute x equal to 1 here. So 1 equal to sin square theta means sin theta is 1. Sin theta is value 1 when theta value is pi by 2, because sin 90 is 1. Now the limits are exchanged. So beta of m comma n can be written as theta is equal to 0 to pi by 2, x power m minus 1, x means what? Sin square theta whole power m minus 1 into 1 minus x, x means sin square theta whole power n minus 1 into dx, dx means 2 sin theta cos theta d theta. So this can be written as beta of m comma n equal to integral theta equal to 0 to pi by 2. This is sin power 2m minus 2 theta. 1 minus sin square theta is cos square theta. Cos square theta power n minus 1 can be written as cos power 2n minus 2 theta into this 2, I am writing it outside, into sin theta into cos theta d theta, right? So beta of m comma n is equal to 2 times of 2 theta equal to 0 to pi by 2. Here we have sin power 2m minus 1, here we have sin power 1. So bases are same, powers can be added. So this can be written as sin power 2m minus 1 theta and cos power 1, cos power 2n minus 2, same again, bases are same, you add cos power 2n minus 1 theta d theta. This is the result we have to prove. So hence prove the result, right? Now let us see another property of beta function. Prove that beta of m comma n is equal to beta of m plus 1 comma n plus beta of m comma n plus 1. So to prove this result, let us consider RHS first, then we'll get back to LHS. So beta of m plus 1 comma n plus beta of m comma n plus 1. By definition, we know that beta of m comma n can be written as integral 0 to 1 x power m minus 1 into 1 minus x whole power n minus 1 dx. Now I want beta of m plus 1 comma n. So in this just replace m with m plus 1. So this can be written as integral 0 to 1 x power m minus 1. Here m means m plus 1. So m plus 1 minus 1 becomes m into 1 minus x power n minus 1 dx plus in this second integral beta of m comma n plus 1 is there. So in this definition just replace n with n plus 1. So we get integral 0 to 1 x power m minus 1 into 1 minus x whole power n plus 1 minus 1 is n dx. Now in these two I can take this common, x power m minus 1 into 1 minus x whole power n minus 1. If I take it common, so this is x power m minus 1 into x is x power m plus this total into 1 minus x, that gives this second term dx. So plus x minus x cancel, integral 0 to 1 x power m minus 1 into 1 minus x whole power n minus 1 dx. But this is same as beta of m comma n. So we got LHS. Thus LHS is equal to RHS. So this is one result of beta function. Now we have some other forms of beta function. Let us see. Beta function can be expressed in many ways. This is also, in this way also we can represent a beta function. So we have to prove that result. Show that beta of m comma n is equal to integral 0 to infinity x power m minus 1 by 1 plus x whole power m plus n, or this we can also prove this result also. This is also same as 0 to infinity y power n minus 1 by 1 plus y whole power m plus n dy. Let us prove this result. Again we prove this result by definition, or by definition we know that beta of m comma n is equal to integral 0 to 1 x power m minus 1 1 minus x whole power n minus 1 dx. To get this result, just substitute x equal to 1 by 1 plus y, right? So differentiating both sides, x derivative is dx, 1 by 1 plus y derivative is minus 1 by 1 plus y whole square into dy. Now the limits will be changed. Here, what is the lower limit of x? 0. Substitute x equal to 0. So 0 equal to 1 by 1 plus y, that implies 1 plus y equal to 0, 1 by 0, that is y tends to infinity. So lower limit, when x equal to 0, y tends to infinity, and now upper limit, x is equal to 1, substitute x equal to 1, so we get y equal to 0. So this integral can be written as beta of m comma n equal to integral infinity to 0 x power m minus 1. X means what? 1 upon 1 plus y whole power m minus 1 into 1 minus x. X means 1 by 1 plus y whole power n minus 1 into dx. Dx means what? Minus 1 by 1 plus y whole power 2 into dy. So same again, if I remove this minus sign, the inequalities will be interchanged. So this can be written as integral 0 to infinity 1 by 1 plus y whole power m minus 1. If you take out the LCM for this, 1 plus y minus 1, so this is y power n minus 1 by 1 plus y whole power n minus 1 into 1 by 1 plus y whole square dy. So beta of m comma n is equal to integral 0 to infinity, what we have in the numerator, y power n minus 1, y power n minus 1. Denominator we have 1 plus y power m minus 1, 1 plus y power n minus 1, 1 plus y whole power 2. So if you take out the denominator, 1 plus y, all the bases are same, so powers can be added, minus m minus 1 plus n minus 1 plus 2. So minus 2 plus 2 cancel, this is 1 by 1 plus y whole power m plus n into dy. So this is what we have to prove. So we prove this result. So these are the other forms of beta function. Let us see problems on beta function. Express the following integral in terms of beta function. We have to represent this integral in the form of beta function. So for that, let us take x square equal to y. That implies x is equal to y power 1 by 2. That implies dx is equal to 1 by 2 into y power 1 by 2 minus 1 is minus 1 by 2 dy. Now, what is the lower limit of x? 0. If I substitute x equal to 0 in this, I get y equal to 0. And upper limit, if I write x equal to 1, I get y is equal to 1 square, that is 1. Therefore, this integral 0 to 1 x dx by 1 minus x square can be written as, when x equal to 0, y is 0, so y equal to 0. When x equal to 1, y is equal to 1. X dx, x means y power 1 by 2 into under root of 1 minus x square. X square means y. Dx, this dx can be written as 1 by 2 y power minus 1 by 2 dy, right? So this can be written as this 1 by 2, let us write it outside. Integral 0 to 1. Here y power 1 by 2 is there, y power minus 1 by 2 is there, both is cancel. So 1 minus y whole power 1 by 2 minus 1, that is minus 1 by 2. I can write it as y power 0 dy. So this can be written as 1 by 2 into integral 0 to 1 y power m minus 1. 0 can be written as 1 minus 1 into 1 minus y whole power n minus 1. This can be written as 1 by 2 minus 1 dy. So this can be written as, this total integral can be written as beta of 1 comma 1 by 2. This is what is asking, express this integral in terms of beta function. So we got this integral in the form of beta function. Let us prove this result also. Prove that integral 0 to 1 x by 1 minus x power 5 under root dx equal to 1 by 5 into beta of 2 by 5 comma 1 by 2. Let us prove. So let assume x power 5 is equal to some y. X power 5 equal to y. So x is equal to y power 1 by 5. So if you differentiate both sides, we get x derivative dx. So 1 by 5 into y power 1 by 5 minus 1 into dy, right? So this can be written as integral 0 to 1 x dx by 1 minus x power 5 is equal to, so if I write the lower limit x equal to 0, y is also 0, and if I write upper limit x equal to 1, that implies y is also 1. So integral 0 to 1 x into dx, x means y power 1 by 5 by under root of 1 minus x power 5 means y into dx, dx means 1 by 5 y power minus 4 by 5 dy, right? This 1 by 5 write it outside. So this integral can be written as 1 by 5 integral 0 to 1. Here we have y power 1 by 5 and y power minus 4 by 5. So this can be written as y power minus 3 by 5 into 1 minus y. Under root of 1 minus y means 1 minus y power 1 by 2. If I take this to numerator, minus 1 by 2 into dy. So this can be written as 1 by 5 into integral 0 to 1 y power m minus 1. So I want m minus 1 equal to minus 3 by 5. So m equal to minus 3 by 5 plus 1. So m equal to 2 by 5. So y power 2 by 5 minus 1, right? 2 by 5 minus 1 means you get minus 3 by 5. into 1 minus y power 1 by 2 minus 1 dy. So 1 by 5 into this total integral can be written as beta of 2 by 5 comma 1 by 2. This is what is asking to prove. So hence proved. Okay, let us discuss about the gamma function in the next class. Thank you.